Alright, time for another draft physics video presentation. DraftScience here on YouTube. Yeah, says it up there. Anyway, so Google and the Baldy Cats thing, I guess I'll let it go. You know, I've done enough videos stating the point. So, you know, maybe just periodically I'll go back to the subject of both Google and how dysfunctional it is and how much it sucks, which came up in the comments section just because there was comments by a couple of different people. You know, one guy posted like 8 comments on one video or something, you know, and they're all nonsense. And then the other was troll stuff and, you know, just junk. And usually by accounts that are, you know, less than a week old. And, you know, YouTube just ought to give you that function just to say, no thank you, you know, to any comments by accounts just created for this purpose. Obviously from people who've already been blocked or for some other reason don't have legitimate accounts or don't wish to use a legitimate account. I mean, it just should be a feature that I just turn off comments by accounts obviously created for the purpose of just making fart sounds and whatnot. You know, it's just fake people doing little fake things. Yeah, should be a feature. Anyway, I mean, if, you know, you could just go through the list of about 1,000 things or maybe 10,000. Oh, if I ran the company, how would it be run? You know. And Google is so unimaginative and, you know, featureless and dysfunctional in so many ways. They have all the power, we have none, and the trolls, of course, have lots of power. The hecklers, they put megaphones right in the audience so the hecklers, you know, can disrupt whatever the show is. It's that bad, really. So anyway, and then the Baldy Cats thing. So yes, he's just a despicable coward, the whole shill thing. It's sad that that works for people, you know, that people who are smart want to listen to a bunch of jerks talking, you know, playing little drinking games and, you know, I mean, it's so juvenile. You know, it's almost ironic what humans have become, you know, in terms of, you know, this is something you wouldn't expect even from, you know, buffoons in a dorm somewhere at college. But you'd say, yeah, look what that is even turned into. You know, I mean, nobody on this planet's taking any part of their obligations here seriously, and it's because that has been popularized. Being an asshole has been popularized as what you're supposed to be. You're not supposed to be, you know, somebody useful and productive. You're just supposed to be some asshole who has a bunch of stories about being an asshole. So anyway, it's just so ironic, you know, in that Baldy Cats was a teacher and he doesn't even get it. You know, that, you know, you have the power to influence people, and what are you influencing them with? What kind of, you know, what kind of show are you presenting to be mimicked or imitated? I mean, what kind of role model are you? Yeah. And you should be more aware of it if you were in the business. And the key word is were, apparently. So anyway, so now he's just in the business of feeding assholes. And doing it as a person of low integrity. Again, coward, just as a gross coward. Clearly he was afraid of the debate and he weaseled out of it with a cheap, silly excuse. And, you know, just a piece of crap as a human being. Anyway, but so typical, right? Just typically human, you know, something you'd expect from the religious. Anyway, which they are, frankly, the science types. The science has been, you know, a long time ruined. And again, Bohr, the religious nut, won the debate. And it's just sad that science is just not worth the trouble. We have to relabel the idea of finding the truth because scientists really aren't in that game. Anyway, so we'll do some comments that provoke a couple of subjects, so might as well go with those because I don't feel like making a specific subject video yet on these subjects. So we'll just, in a draft manner, discuss the strangenesses, the stuff that doesn't make much sense, the conflicting evidence. So there we go. So we're just 2 comments of anything. So I'll talk a little bit about, Linux, just because it came up here. So, edit. If the folders disappear, always the standard ones. Yes, that's true. Then maybe the bug is blah, 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 which is disabled by editing blah, blah, blah. So, yeah, that might prevent it from happening in the future. I don't know. I don't know where you got that from. But, because I really couldn't find much on the subject, frankly. So preventing it is fine, but it's not going to fix what it already did. So we'll see if that does work in preventing it. Sort of. I mean, I haven't had the problem for like 3 months or more. So whatever it is, it's a fluky little bug that just, it's, horrible when it shows up, but it doesn't show up too often. Anyway, regarding the folder that disappeared, you could somehow move the search. Yeah, I did all this searching crap, and the fact is Linux doesn't have great tools for fixing problems. The tools usually get you deeper into the problem. I mean, you wanna really get into trouble, try to fix something that's broken in Linux, and you can just forget it. You can just start over, because the fixes often just break stuff even more. So, but I've already been there and done that. So whatever it's doing, it's deleting it. It's not, it's not hidden somewhere, and it's still intact and all that kind of crap. I mean, these are just hard drive labels. I understand all that. But as soon as you reboot, it starts rewriting. And again, anybody who's done this, file recovery stuff kind of knows that, the files are in pieces all over the place. Putting it all back together again is just such a waste of time. You just won't get what you're looking for. So unless it's, I don't know, the combination to your, or some, unless the information you need is like your safety deposit box combination or some kind of weird thing that, there's $1 million in there and you desperately have to get the information back. Generally speaking, it ain't going to be worth your trouble. I'm just saying from my personal experience. You want to watch the hard drive actually smoke and the disks fly out, then go ahead and try using recovery tools. Go ahead. Because that's what you'll get in the end. You'll just get a dead drive. Anyway, and then he mentions that he uses Firefox for Android and he dislikes the changes. I just found it unusable. I mean, I can't get anywhere. You can't, you have to click 2 buttons just to refresh. I mean, it's so stupid. You have to go to the menu to hit refresh the page. I mean, no, I'm not doing that. I mean, the key thing is, I have all my stuff is broken. I mean, I buy stuff that's broken, and I either fix it or I learn how to use it broken. So, I mean, I have a tablet that's, I have a couple of them, and they're cracked screens, so only half the screen works. So, if the refresh button isn't there, then I have to turn the tablet upside down to get to the menu to open the refresh. I mean, it's just too much trouble. Too stupid. I mean, it's just such a, and they got plenty of room to leave the button where the fuck it was. Why take more buttons away and hide them in menus when there's plenty of room for them? Like the tabs, for example. Anyway, no need to go on and on about that. So some asshole made some sort of comment about how I'm too much of a moron to use Linux, and I'm using Linux, and I actually have a video that's at 20 frames per second, which is almost impossible to do with the regular tools Linux provides. Okay, so you can do your little raggy crap, but a lot of Linux distributions are really bad at this video thing. And if you do any research, and the fact is I'm using a program that nobody uses because it'll fuck up your computer. But I'm able to use it because I had to make tools to prevent it from wiping out all my hard drive space and doing other things that were quite negative. So I'm not exactly I don't need things made safe and big giant smiley face buttons and all that kind of crap. But the truth is, Linux has a lot of issues. I mean, that's why people don't use it, is because it does need to be tweaked. You can't just put it on your computer and say, there, everything's fine and working, unless the only thing you want to do is, open a web browser. If that's all you want to do, then fine, it works great. But if you want to do a little bit more than that, yeah, you're gonna have to play with it a little bit to force it to do it, because the standard tools don't do it very well. Fuckhead. Anyway, so on to the Big Bang. Okay, so I mean, people always got to say things excessively, right? I'm saying there's very little evidence, and it's really hard doing this. Well, how did the universe start? Bullshit. I think it's questions that people shouldn't even bother with, because we really don't have enough information. We kind of know, though, that what the answer is going to be. It's like abiogenesis, figuring out how the first DNA molecule got going and all that kind of crap. It's interesting to think about it. You go, oh, yeah, I wonder. But what's the point? Because the chemical circumstances, how the first membrane got formed and all this stuff, it's not going to be available information. It's going to be difficult, and there's just no point. We know basically the idea, okay? I mean, we have enough pieces of the evolution to describe it. You really don't need to know, well, what was the first humanoid mother's, what was the meal she ate before she gave birth to the first human? That kind of thing. Is there some point? What the process was, okay? That the first human with less chromosomes, was a human, We know it was a person, and it came out of something that wasn't quite a person. All right? It's this chicken and egg crap. You really don't need to do this. You know that a chicken laid the first fucking egg. Okay? It wasn't, we know which one came first. Sort of, in the sense that it had to be a broken chicken because it made an egg, a broken whatever it was. And so it was so broken as a whatever because now it laid an egg. But whatever. So yeah, the Big Bang. So actually Big Bang is nothing but Genesis rehashed as physics formula. There's no formula, but besides that, it's just this, you're posing a rational question. How did it happen? That's reasonable. And there's all kinds of speculation. The point that's obnoxious about physics is that they think they have the answer. They think they know. They know with a certainty. And they have little tiny evidence to support their certainty. And that's the subject that's really important. And so this gets to the whole cosmic background radiation, which, is an interesting subject in the light of what I've learned in the last year. Because scatter can change frequency, and so that's something to talk about, and how it does that, and how you might understand, how light can be degraded traveling through the universe, because the universe it is not a perfect vacuum, especially when you go into galaxies and through things and by things that have produced little bits that are still floating about in the crud. And you have a high likelihood that you're going to run into these atoms, and that your light's going to get scattered to some extent. And through the scattering process, it's going to be, its frequency is going to be changed. Now, the whole Big Bang thing, like I said, never made any sense to me because, so might as well get to it. Uh, so anyway, so it's kind of just an excessive thing. This isn't it isn't as bad as writing a silly book of Genesis. Okay, it's it's just bad that they're saying that it's the truth and it's just a story. It's just one story, and there's lots of ways you can um, take the facts and create a different story. And the fact that they have somehow decided they're not going to consider any other stories is the part that's just the huge failure of the science. That's what makes it a religion. But yeah, I guess I just wouldn't compare it to Genesis. That's just going too far. I mean, just make the point that they have little evidence and insane arrogance, okay, in describing events. So, okay, so you start with this idea of a Big Bang, and it doesn't make any sense that, okay, let's say that the universe was a small thing. Now, the idea that it was so small that all the matter was in one place is, in my opinion, silly. You could understand that it could be, that all the protons and electrons were lined up, proton, electron, proton, and they were stacked next to each other in such a nice arrangement that they were very compressed. Now, that's understandable. But anyway, it doesn't really matter. The idea is that all this stuff flew out of some beginning. Well, the obvious thing is the light bits would fly very fast. The energy force, the light. Okay, the speed of light it's moving, right? So it's leaving the bang. And we're obviously made of stuff that took a while. I mean, it's lagging behind because it's matter. And so you're like, what are you talking about, Big Bang? How are we going to see the Big Bang? It left the building. I mean, the seeing part is way gone. And you could have some idea that, okay, well, some of the parts you see bounced off the matter, and then they bounced off matter, and they bounced off matter, and so they're inside here. Yeah, you could get that. But that wouldn't account for the stuff out here. And, so it just gets kind of like, it doesn't make much sense. This even distribution caused by a bang, and we're somehow, getting an even distribution. I mean, how can it be an even distribution? There has to be an inside and an outside to a Big Bang. So I would argue that an alternative theory is just that the universe is made out of this stuff I've called force, and that when matter is compressed, okay, it's basically trapped more force. So you could even go back to the simple diagram of the atom, and the idea of you have a positive protons and neutrons in the middle there, and even the electrons. The electrons in the inner orbit are the ones with the high energy, a lot of pressure, because they're resisting falling into a proton that they're much closer to. So they have a lot of go this way, go in incentive. And the only thing that's going to keep them from going in is the amount of pressure between the electrons. So the pressure is going to be higher between the electrons. So the high pressure is in the small parts. Okay, so the more contracted, the smaller, the more you compress the matter, the closer you bring it to each other, the more energy it has. So it's like a simple ping pong argument that the force has more energy when I trap it in a smaller area. Okay, and also what's happening, it has more energy in the sense that there's more potential energy. Okay, but the other key thing to understand is that each interaction means the force has been degraded a little bit. That is, it's been obliged to move a piece of matter, and moving matter absorbs the energy. And so in one sense, the force is having its energy absorbed, and that's what's causing gravity. So anyway, the point I'm attempting to get to is that you could understand the universe as being something like galaxies that we see very far away are small and brighter. So they're brighter and smaller. And the ones we see that are closer are, let's draw them in some way that you could understand. So there's a galaxy in the traditional sense, okay, stuff orbiting around. They're bigger and less bright. Alright, so you could say they're expanding and contracting. And you could understand that as being, well, what's the universe doing is that gravity itself is actually changing. That as the universe contracts, it means it absorbed energy from the universe, okay? And as it expands, it's giving energy back. So it's really just about the inside and outside pressure. And so all you're saying is that when the energy's out here, okay, there's more gravity. When the energy's in here, right, and there's less out there. So it's just a yin-yang thing between the pressure. So the universe just goes through cycles where it expands and it contracts in a graceful kind of way. You know, the galaxies get bigger, and then as more energy gets outside because they've expanded, then there's more pressure pushing them in, so then they contract again. You know, they just go through this contraction, expansion, contraction, expansion. So that's an alternative explanation that works. Alright, so anyway, let's get to this cosmic background radiation, which essentially is the understanding that if the universe goes further than 13 or 14 billion light years, that there would be all kinds of objects producing radiation, you know, light, that we could see. But unfortunately, the light has to travel 13 billion light years. And sort of the argument is that it's now gotten redshifted out of visibility. That stuff further away gets redder and redder and redder and redder, and it gets to a point where it goes invisible and then starts becoming microwaves eventually. So you could argue that the further away, the less you're going to see of it, and that what's really happening is that the light, as it travels distance, is shifted. Now, so their argument is the whole universe is expanding. That means that, you know, I'm getting further away from the camera. Everything's getting further. Every single atom is moving away from every single other atom by some speed, and the whole universe is expanding in some kind of bizarre way because more space is being made. So it's not like two things are sitting here minding their own business and they have some real velocity. They actually think more black space on the board is being made, and the two things are moving away from each other without having a real velocity. And that's happening to the photons, so that the waves, you know, they think they're waves. You know, the waves are stretching because the space is stretching. So the distance between the nodes is now further because, you know, space has introduced itself constantly into the photon and made the photon stretch, which is just, in my opinion, a silly story. I mean, that's just silly. So anyway, so I would argue that the distant object sends light, okay, radiation, and the fact is the universe does have a lot of little hydrogen atoms in it and other kinds of atoms, and these physicists know that Compton scattering, that is, as the light hits, see, I would argue the light's a bunch of little bits at a frequency, and what happens is one or two of the bits aren't in perfect alignment, so they're polarized. So there just happens to be a hydrogen atom here, and so this bit hits it and scatters in a direction. Now the scatter has to do, there's momentum arguments. So if this doesn't have any momentum, it's moving very slowly because it's just a hydrogen atom in space and nothing's hit it a lot, and so it doesn't, you know, well, let's just say for the sake of the argument, it hits it and it just gets a tiny bit scattered. It doesn't get a lot scattered, just gets a little scattered, you know, changed in its direction through the process, and the atom gets a little momentum as part of the exchange. But the real key thing is that this takes time. It takes time to hit the atom, move the hit the electron in the atom, sorry. Okay, it's really hitting the electron in the atom, and that the electron moves a little bit of distance slower than the speed of light, so it takes a little time for the one little piece of the photon, let's just put another bit here, just so you get, it can be any one of these bits that gets scattered at any time. And so that little bit now that should be in this position, okay, is now in this position. Whoops. slow it down. I got to put it back here. So it's a little bit out of position. And, you know, you can understand that as all these little bits are probabilistically, they're all going to encounter the same event. So all the little bits eventually are going to get scattered, and they're all going to get scattered a different amount of times. They're going to hit something a different amount of times. But you can sort of understand that each time they do, they get slowed down, so that it's pretty easy to take light that's got this frequency, all right, and convert it by just merely putting it back together. That is, you've scattered it, and you've scattered pieces in all the same angular direction, or a similar one. And so now you have a piece. The arrangement is that this one was behind, and you didn't even bother redoing that one. And you put this one in, and you put this one in. So you've created a new frequency, you know, that's delayed, but it's still going the speed of light. It just was slowed down because each bit had to be scattered. And now you have a new frequency that's a little bit longer. So again, this is something they know happens, you know, that they can send light in to small particles, you know, a field of small particles. You know, they can put the light in, you know, and it's usually a lot of photons in, you know, more than one. It goes into a field of bits, and it comes out, okay, so it went in as this frequency, and it's going to come out as a little bit changed, depending on how much stuff I have in there. And, you know, that's a perfectly reasonable explanation. So in a sense, this is the tired light argument, that the reason why it's red shifted is because it had to actually move some electrons, and the electrons slow it down. It actually slows the light down because the light has to now move the electron, and the electron moves at a slower speed, and the electron will release the photon. So it's like a bird. It's going 50 miles an hour. You lasso it, and it drags you on a skateboard. Now, it's going 50 miles an hour, but dragging you on the skateboard is going to slow it down quite a bit. And then the bird gets out of the lasso and goes back to going 50 miles an hour again. You know, it's that kind of thing. You've stolen a little bit of its energy by, you know, having a little period of time where it had to drag you along. And the same thing is just happening to the photons, the pieces, the force bits that make up the photon. They've been slowed down just a little bit, and in that process, it's widened the distance between them. And so you can sort of understand that there would be a proportional relationship between how much space there is, you know, how much distance you're going, and how many scattering events you're going to likely, you know, probabilistically incur. And so there would be an obvious proportion. So you can understand that, yes, light traveling a long distance redshifts. And it makes perfectly good sense, and just has to do with how far the light had to travel, and it doesn't have anything to do with space expanding, or the object actually moving away from you, or you moving away from the object. It's not that kind of redshift. It's a redshift because the light itself, okay, had to go through interactions with matter, with electrons, and that absorbed some time, and that time is reflected in the increase in the distance between the bits. And so it makes perfectly good sense, frankly. And so it explains, it answers the question, and I don't think there's any reason to believe it's not a satisfactory answer, or just as good as, well, I'd say it's better than, because it doesn't rely on some magical event that expands space. Some weird notion that somehow the space is getting fat, you know, or, I mean, it just doesn't make any sense. Space, you know, more space, it just doesn't make any sense. I made more space. Space is expanding for some non-explained reason. It just doesn't make any sense. There's velocity or no velocity. You can't just say, well, it doesn't really have velocity. We just made more space. We blew up the balloon. I mean, it's just not a good explanation. All right, so the other thing I've been thinking about is the electron gun. And the funny part is, it's exactly the same as the proton gun, as the X-ray gun. They're all the same guns. All right, and all it really is that you put an electrical potential, okay, on a heating element. All right, and the element ends up having the charge of the voltage you put on it, so it's going to be net positive. So you're putting a voltage on it, and then you have a negative anode. Is that how? No, they use a positive anode. Okay, and this has the negative voltage because it's tied to ground, right? That's traditionally how it's done, but you can do it the opposite way. It's just trickier. But anyway, so so you heat this metal, which is, you're basically just saying that, when you got it heated so it starts glowing, it's producing, okay, that it's falling apart, okay, that the atoms are degrading in their arrangement, okay, and then after you cool it, you might not have the same amount of mass that you had when you started. You're actually degrading the element, and it's that kind of heat. A little bit of heat won't do it. You have to have enough heat that you're really making a mess out of this thing, and you might even burn the filament out in a few hours, especially in air, in an oxygen atmosphere. You might just catch this thing on fire, so to speak, and you'll really be degrading it. But anyway, the point is you've got to degrade the element, so you're really pushing it in the sense that there's an obvious circumstance where you're obviously sending atoms out. Okay, you're releasing them. The atoms are coming off the surface and going into the atmosphere, and they might go right back down again. But the point is that it's like the corona of the sun. It's going to be an area full of a plasma. Okay, so you're creating a plasma essentially here at the surface of the electrode, the coil. And so you have this plasma of atoms that are, semi-disconnected. They're almost still part of the filament, but not quite. Okay, they've been ejected, they've been released, sort of, and they can, like I said, they can go right back in. Or if you do create this, well, then they can be moved, and they can be moved because they're ions. Now the tricky part is ions can be polarized ions, depending on what the material is, what the atom is. So the idea is the idea of an ion is that you have an even amount of atoms. Like to have everything square. Square, not square is a literal thing. I mean square in the sense that there's as much negative charge as there is total positive charge. So you've essentially created an outside that compensates for what the inside is doing. The inside is saying go in, let's say, to an electron. The outside is saying go away, and that theoretically, from a distance, say this distance, the two forces would seem equal. The away force equals the go in force, and so you have zero potential. And so most atoms achieve that kind of a state, or something semi-close to it. And so the question would be, is that when you create an ion, what are you doing? And the ion would be that you've now have the proton. Let's say I've ionized it, which is now I only have 3 instead of 4. And so now I sort of have an imbalance because there isn't as much negative to compensate for the positive. And so now I have a positive ion, in the sense that from most places it'll look positive from out here. But the point would also be is that from certain perspectives it's going to look like different things, an ion. So anyway, so it really does depend on whether this void remains a void. So you could theoretically have an atom that just changes its composition and now becomes a dipole, where one side is very positive and one side is very negative when you've ionized it. So you've made something that's more like a magnet. And I would argue that that metals likely create polarized ions. Ions that do have a plus side and a minus side. Not that they are, plus, 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 or minus, 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 minus. See, if it has an extra electron, then you can argue it's a negative ion. because it's got extra negative. So instead of 4, it has 5, and therefore it has more negativeness from a distance. But anyway, so, it's a little bit, there's reason to wonder, whether all ions are the same. But anyway, so the point is if it's just a regular nonpolar ion, well, then you could say, yes, it's just going to go from the negative to the positive. So if it's a negative ion, it's going to be attracted to the positive anode, and it will travel that distance fairly easily. I mean, it'll have a real reason to leave the plasma and go there. Because it's an atom, it can move. Okay, but the question is, if it's an electron, how does it move? If it's just an electron or just a proton. So I would question whether you can actually move just protons and electrons from the positive to the negative. I would question whether you can even make them just by heating something. So anyway, so this goes back to a lot of other questions. So the trick is that all these experiments all take place in some kind of vacuum, but it's not a perfect vacuum. So, and the one that kind of gives it away is what do they call it, photometer? I don't know what the little thing where you put a shiny side and a dark side, on a little needle, and the thing could spin around. Well, when they do this, if they put it in a strong vacuum, nothing happens. They have to actually have some atoms in here for it to spin. The atoms end up showing you something that doesn't have anything to do with the underlying physics, in the sense that it has to do with the fact that the atoms are creating a reflective place for the energy that comes off one surface is going to be photons. The energy coming off the other surface is going to be, it's going to be photons, but it's going to be infrared photons, and the infrared photons won't go through the atoms. The regular photons, the higher energy photons, will go through. So that's what's really creating the pressure difference on the two sides, and that's why you need atoms in here for this thing to work, for this thing to spin. It's because the atoms are just creating a surface that's transparent to one form of energy and opaque to the other form. All right. But the trick is that what it's telling you is that if there's a perfect vacuum, though, that reflections are exactly the same as absorptions. That the same amount of energy actually does reflect. That an absorption is a reflection, in fact. That both sides reflect energy. That's what the real... But anyway, I'm just saying that the experiment can deceive you, okay? Because you could take a lot of the air out, and it works, as long as you leave some air in there. And it stops working when you actually do take the more air out. And so you're sort of being fooled that, oh yeah, in a vacuum it does this. Well, it's not really a vacuum. And the catch is when they make cathode ray tubes and X-ray tubes and all these kind of tubes, they don't necessarily have a perfect vacuum. So they're starting off with gas in, atoms. And this sort of gets to the electricity argument, because lightning, okay, between, clouds and the earth, it's kind of understood now that what happens before the lightning can come across is that there has to be atoms arranged that find a path. So there being a subtle amount of current is coming through and basically aligning the atoms first, and then the lightning takes that path. So once it has to make a conductor first. So essentially, first, electrons just move a little bit from atom to atom to atom to atom to atom and create little bits of ions. And it isn't until it's ionized the path, okay, then the voltage can go, the current can go through the lightning. And then the ions automatically switch back. So the lightning is telling you all the atoms are switching back. That's why they're giving off light. And so it's like the real lightning didn't make light. It's the going back. It's the returning back into a conductor again that's giving off the light. And as soon as it turns back into a conductor again, a path that's got the ions, then the electrons can shoot across it again. and then it goes back, and then they can shoot across again. So you might get 3 or 4 of these, as what you see as one lightning bolt is really a few discharges through the same conductor that it just keeps remaking. Anyway, and so it's sort of telling you how critical, the plasma. So I would argue that what's really happening is that a plasma forms, a collection of atoms. Atoms are being collected. They're being brought to each other by ionization and made more, thicker, and to create a path that now the lightning can take. It's building a conductor. It's taking atoms that are separated and it's putting them together and ionizing them all in a form where now they can carry electricity. And it comes out kind of jiggery because the layers of the atmosphere have different densities, and so with each change in the density, the where you can line up the atoms changes, and so you get that jiggly thing. Alright, well anyway, it's just another example of how much you need atoms to transfer electricity, or in a way to transfer electrons. Alright, so this is a long way to get into it, but it is complicated. So anyway, so cyclotrons, CRTs, X-ray bulbs, proton sources, electron sources, or photon sources, they all use essentially the same thing. They heat a substance, okay, which obviously creates a plasma on the surface, and then they essentially can move the plasma, I would argue, okay, and allow the flow of the electrons through that plasma. And the more consistent your fields, the more straight these lines are. So they're not like electricity because the plasma is actually moving in the same direction as the electricity is moving, and so it can appear to be very straight. So in experiments where they are measuring the mass of an electron, so they take an evacuated tube and then they shoot some electrons in this direction and they put a magnetic field through it, and the electrons take this course. Well, you could argue that these are ions, that the path was created by the ions, and that the ions are showing you where electrons can be pushed, and then you're seeing them reionize. Again, it's the same argument that you energize the atom. To get the photon is the energy going. Let's see how to say it. It's the atom giving back energy. Okay, is the photon. When you see a photon, it's an atom giving away energy. So you kind of have to know that. Well, if it's giving away energy, when did it get the energy? Where did it get the energy from? And so that's sort of a question you can ask. So I mean, obviously you can have instant ionization. That is, something hits the atom and creates the photon. But then you're not going to have the scatterer is going to be, it's going to be a more dramatic diminishment in its momentum of the thing if it created the extra energy, because the atom's going to reabsorb from the thing that hit. It's going to absorb the energy that it's releasing. It has to be balanced in the end. You can't get what you didn't give in some sense. But anyway, so I mean, you could argue that this is just showing you the path that's created because the atoms are going to line up in this way, and now you're just creating a conductor that allows the electrons to flow, and the electrons are creating photons because the electrons are flowing between the atoms and releasing photons. So you create a path out of the ions, out of the plasma. So you're just manipulating a plasma. You're not manipulating actual electrons, is the argument. And the cyclotron does a similar thing. And then even you can go all the way back, all the way to when they do experiments with a radioactive isotope, and you see the little bits fly off, and the thicker ones they're saying are are nuclei, and the longer and dimmer ones they're saying are the beta. The beta are the electrons. But are they? How do they know? And so that goes back to another old experiment, where you create a hole in something, you put a little radioactive isotope in here, so now you're guaranteeing your rays are pretty straight. And then they put a magnetic field, north and south, and they say, oh yeah, some of them go this way, and some of them go this way, and some of them go straight. So that's your gamma, your photons. Well, the question would be is, these are moving electrons, so they shouldn't be going towards and away, they should be coming in and out, right? So it's kind of a contradiction, right? Because when they put the magnet here, they don't tell you that the, which way the beta or the gamma is moving that way or this way, in or out of the blackboard. They always just sort of describe it as, no, these move this way and these move that way. So that seems a contradiction, because they're supposed to be moving charges, so they should be doing the other thing. They're supposed to be just, because somehow electrons are supposed to be little magnets themselves, and have magnetic moments, and so their magnetic moment should force them to move in the third dimension. So it seems an inconsistency there, because then when they do the cloud chamber experiment and they put a magnetic field through the cloud, they'll get this kind of thing. Okay, so here's your radioactive isotope, and the electron beam comes off, and then all of a sudden they'll do this little bit, or this little bit. Okay, and they'll say that's a beta, and this is a that's an alpha positive, and this is a beta negative. When it also could be explained that these are ions. Okay, it's an ionized path that's created in the cloud chamber. That's what's creating the photons that you see. So again, we got the problem that this is sort of a plasma, and you're just manipulating the plasma, and that obviously the energy takes the path that you're created for it. And so you're just bending the plasma and then watching energy flow through the conductor. So you're seeing the path of the conductor, and you're not really seeing the path of energy. The energy is still going in all kinds of ways, and it's completely invisible, because it's not creating ions. It doesn't have enough energy in itself, or it just doesn't do it to the creation of the ion. It's more complicated than just hitting the atom. The atom has to polarize and go through a process. So anyway, so it leaves open some questions. So they got a magnetic field going this way, in and out, and you have this curled thing. So again, it's just saying that, well, why is it curling here, and in the initial experiment it didn't curl? So those two things don't fit quite together. And again, I would argue that you just don't have much evidence that electrons can be moved in, off this straight line and maintain momentum. I would argue they always have to be pushed by something. And so if you move them in this curved path, whatever you're pushing them with would not be there anymore. So obviously they wouldn't have any ability to take turns and go against the energy. That wouldn't make sense for the electrons to be able to change direction entirely. So it's something to think about. Anyway, but the idea is, the fundamental argument is there really isn't any way, and the way they capture these things is to use some material that fluoresces, that is, that releases photons. So they detect electrons, they detect protons, and they detect photons, all with a material, okay, that with the same thing. So you can't be sure when you see light coming off a surface, you can't be sure it wasn't hit by an alpha, beta, or gamma. It could have been hit by any one of those. Any one of those will create a reaction in the material that says, photon, energy hit me, energy hit me, energy hit me. And so it gets a little dicey being able to distinguish between an X-ray, hitting having a material that can tell the difference between a photon that hits, or tell the difference between, an X-ray, okay, or an electron. I mean, the how the thing's going to react is going to be kind of the same, whether an electron or an X-ray hits it. It's going to be the same output. You're going to get the same information back for either one of those events. So, there's a real question whether you're just measuring the energy that gets to the surface, or whether you're actually measuring electrons. Are you just measuring the force that might have pushed an electron, or are you just are you measuring the energy that pushed an electron, or are you just measuring the energy? Because the two are going to be very close to the same thing. The momentum of the electron is essentially dictated by whatever pushed it. So if an X-ray pushed it, it's going to have essentially the same energy as the X-ray. So how do you tell the difference between the two things when they hit a target? And we really don't have a device that does that, except to measure charge. So the real test, the real way you need to do it, is to understand that the electron is charged. So when the electron hits, it will create an excess of negative charge on that surface, where when the X-ray hits, it's not charged, so it's not necessarily going to charge the surface unless it ejects an electron. It could make it positively charged, but it can't make it negatively charged. So you know that when an X-ray hits, I'm not going to change the charge of this surface, unless I'm ejecting an awful lot of electrons. So as long as I don't eject electrons, that would be a way of telling, is if the charge gets more and more negative, you could say you're adding electrons and not just adding energy. But that's the trick, because if your energy is ejecting protons, like heat, well, then it's going to go negative because you ejected protons. So it's really kind of complicated. And so they tell you that this is what they know, and they're sure and they're confident. But I would argue that this, like the two slit, all of this crap has been thoroughly underanalyzed. They really haven't thought about what actually is happening when this coil heats up, that it actually is creating atoms, that the atoms are likely to be ions. The ions are going to be attracted to any voltage difference. At least half the ions are going to want to go in that direction. And I say it could be more than half if the ions are actually polarized. If what you've actually done created a polarized ion, that it'll switch, it'll move just like a magnet. It'll flip to negative to positive, and then the negative end will go right towards the positive end of the anode. So, that's probably enough just to explain that there is some doubt about the conventional notions. When they say electron gun, it really doesn't mean electrons. It means protons, it means X-rays, it means a lot of shit is flying off of that surface. And they can't be sure. They can't filter for just electrons as much as they would like to think they can. There's every reason to believe that it's more complicated than they're letting on. Their simplistic description isn't the reality. Just like the young two waves don't create the double slit experiment, their model and their math doesn't necessarily turn into anything you can draw rationally about what's happening to the atoms on the surface of the heated element. And like I said, you can just know that the atoms are becoming disconnected from the material, and they're just as easy to provoke to move across a charged field as electrons and protons would be, because the atoms are ionized. They're missing pieces. That's how you broke them off the surface, is you took two atoms that were sharing an electron and you ejected the electron, one of the atoms, and one of the atoms now is an ion. It's missing an electron. So you're ejecting ions, and yeah, ions move in a magnetic field, and they also moved in a charged field. So anyway, So enough of the video. So only just two subjects that are still sort of drafty, but you know, I will make subject videos on those subjects, and I'll just fix them as I need to. But I guess it's just trying to work it out for myself about what points need to be emphasized about why there's every reason to doubt when they say they have an electron gun that it's really electrons. Yeah. And such. So, till the next time. And such.